My name is Alexey Kopytov. I'm also known as Mr. Sysbench, and I will be talking about Sysbench. More specifically about some new, recently developed features and how you can use them to do some pretty cool things. I'm going to start with a brief tour into Sysbench history. For those who don't know, Sysbench is a load generation tool. It started as an internal project in the high-performance group at MySQL AB. The very first version was written by Peter Zaitsev. I took over the development, soon after joining the team. It originally included an SQL level benchmark, which we called OLTP for the lack of a better name. There was also a file system level benchmark and a number of micro benchmarks that I will not be covering in this talk. And the tool proved to be very useful in identifying performance problems, troubleshooting customer issues, or just creating repeatable test cases for other people, other engineers to investigate further. And during the early days, I got a lot of feature requests. And most of them were internal, even though we did have some external users, some external feature requests. Most feature requests were internal, and most of them came from Peter. Some of them had non-trivial interdependencies, and that led to growing code complexity. It soon became obvious that it is impossible to cover all possible use cases, cover all possible benchmark scenarios that users and Peter may come up with in a single monolithic C application. And in fact, the code was barely maintainable by 2006. So the solution to the problem that I came up with was also kind of obvious. Let's make it scriptable. Let users define their workloads in some kind of high-level language, high-level API, and let Sysbench do all the heavy lifting, like managing threads, collecting and aggregating statistics, generating random numbers, and providing the DB abstraction interface, because Sysbench supports multiple database backends. As a result of that, the OLTP benchmarks in Sysbench were rewritten as Lua scripts and Sysbench 0.5. Why did I choose Lua to implement scripting? The major reason is that Lua is incredibly fast for a dynamic language. Some people call it the speed queen of dynamic languages. It is also designed to be embedded into C or C++ applications. There's a simple, straightforward protocol that one can use to call Lua code from C code and vice versa. It's also simple and elegant, but powerful. You can do fairly complex things with just a very few, very simple underlying concepts. And seriously, Lua is a beautiful language. If you're not familiar with it, I encourage you to learn it. For a quick start, I can recommend this link titled Lua in 15 minutes, which explains all the basic concepts in a very condensed form. So how did this Lua scripting thing work in Sysbench? There was a number of predefined hooks that you could implement in your users could implement in their scripts. And they were called from C code by Sysbench. There was also an API for SQL and random numbers and strings generation. Those functions were written in C, and Sysbench exported them to user Lua scripts. In this example, I'm implementing three hooks called prepare, event, and cleanup. The prepare hook is called by Sysbench when you execute it with the prepare command. And what you usually do in the prepare hook is to generate the initial data set for the benchmark, like create tables and populate them with data. Likewise, the cleanup hook is called when you call Sysbench with the cleanup command, and it basically returns the database to its original state. And the most important and the only mandatory hook that Sysbench expects you to implement in your script is called event. It basically defines your workload. When you call Sysbench with the run command, it creates the specified number of threads, with each thread calling the event hook in a loop. Sweet and simple, right? And even with this simple and limited API, I know that sysbench worked well for a wide range of use cases. It was used by many users and companies to benchmark MySQL or MySQL forks or MySQL storage engines and compare their performance. Or I know that some companies have implemented large repositories of Lua scripts as a part of their internal QA. I stopped active development after moving to the MySQL development department and later to Percona. I was busy with other tasks. I didn't have enough time to work on them, even though I tried to address occasional bug reports and some simple feature requests. And starting from about 2012, I started getting reports about scalability issues in sysbench itself. There's when people try to use sysbench to benchmark MySQL on some high-end hardware, for example, with CPUs, with tens or even hundreds of CPU cores, then sysbench itself became the scalability bottleneck. But finding time to look into those issues was challenging, and on top of that, I didn't even have access to that kind of hardware to look into those scalability issues. Things changed around last year when I again started working on projects that required me to use sysbench on some powerful hardware, and that's when I hit all those limitations, scalability issues in sysbench and also some functional limitations. And after sitting down and analyzing all those issues and requests, I came to the conclusion that it would require a major refactoring effort to address all those requests. So it took me a few months of rather hard work, mostly in my free time. And the first release in the 1.0 series was made in February this year. Let's look at what's new in sysbench 1.0. First of all, it is the first release in more than 10 years, because sysbench 0.5 has never been actually released in a formal way. It has always existed as just a source code branch, which worked for me and apparently other people, but that made distribution packagers unhappy, because distributions need a formal release with a tag and a changelog to package it and make it available in the distribution. And that's why most modern Linux distributions still offer a very old, outdated sysbench version. But now that I'm back to regular formal sysbench releases, things are going to change, and I think next versions of popular Linux distributions will provide sysbench 1.0. But you don't have to wait for that, because now I provide precompiled binary packages for sysbench myself, and they're hosted by Package Cloud and built automatically for each release for most popular Linux distributions and a number of CPU architectures. sysbench 1.0 also has much better single-threaded performance and scalability, and also a number of functional improvements. We'll go over them shortly, but let's start with performance. So the first question I had to ask myself when I started working on performance issues was how to measure the overhead of a benchmark. In other words, how to benchmark a benchmark utility. There are probably many ways to do it. I implemented this option called MySQL dry run. What it does is it basically tells sysbench to do all work required to generate queries, but do not actually send them to the server. We exclude the server, we exclude the communication overhead, we exclude the client library. Just let sysbench have all CPU resources at once and see how many queries or transactions per second they can generate. The more, the better. This chart shows single-threaded performance, comparing sysbench 0.4 implemented in C, purely in C, sysbench 0.5 implemented in Lua, in plain interpreted Lua, and sysbench 1.0 implemented at Lua JIT. So the main change in sysbench 1.0 that allowed this kind of speed up was a migration from Lua to Lua JIT. As I said, Lua, some people call Lua the speed queen of dynamic languages, but Lua JIT takes it to a completely new level. It's a tracing JIT compiler for Lua, and under some circumstances, it's possible to achieve native code execution speed. Lua JIT also allows faster call from Lua to C by bypassing the standard protocol provided by Lua to call C functions from Lua and vice versa. Basically, we can do native calls into the C code and exchange native C data structures as well. I also did some optimizations in the event loop. Sysbench now uses a faster random numbers generator. Previous Sysbench versions relied on the systemc library to generate random numbers. As it turns out, that is sometimes suboptimal, has suboptimal performance, and the system, the random number generator provided by the systemc library has some poor statistical properties, and most importantly, it doesn't scale. So all those issues have been resolved by moving to a bundled random numbers generator. As a result, the new Sysbench is 3.5 times faster than Sysbench written in C, and about 6.5 times faster than Sysbench with interpreted Lua. In terms of scalability, improvements are even more dramatic. I think this chart speaks for itself, or as Dmitry Kravchuk says, no comments. And some changes in Sysbench 1.0 that allowed this kind of improvements was, first of all, using the concurrency kit library. It's a C99 library implementing some atomics and synchronization primitives, and also some log-free and wait-free algorithms. Basically, that library allows Sysbench to run efficiently on modern CPUs. I also removed mutexes and shared counters, at least on critical code paths. There are also a number of changes in the command line syntax. It has been simplified. For example, in Sysbench 0.5, there was this a little weird option called test. It was the only mandatory option required by Sysbench, and you had to use it to specify a name or a path to your benchmark. You don't need to use it in Sysbench 1.0. You can just pass a name or a path to your Lua script on the command line without any options. Or you can even use the standard Unix hashbank mechanisms like this by making your scripts, Lua scripts, executable without explicitly calling Sysbench. Which is a minor change, of course, but it makes Sysbench look and feel a lot more like standard Linux or Unix utility. And if you look carefully, you'll notice that the command argument is now also optional. So what Sysbench does is when you give it a Lua script but do not specify any commands, it will just pretend that it's a regular Lua interpreter. That is, it will just execute the script without creating any threads or calling any predefined hooks, like a normal Lua binary would do. Which means that Sysbench can now be used as a general purpose Lua interpreter. It may seem like another minor change, but it has some important implications. I will be talking more about them later. Another problem related to command line options that is fixed in Sysbench 1.0 is that in the previous Sysbench versions, there was no way for Lua scripts to declare their supported options. And Sysbench just converted all command line options to global, exported all command line options as global variables in Lua scripts, which was a nice hack, but the downside was that if you make a type on the command line, Sysbench would happily accept it, and your Lua script would just use a default value for that option, which was a source of frequent complaints and bug reports from users. And default values were also handled manually. You had to write some special code to assign options their default values. In the new Sysbench, scripts can declare their options, so Sysbench can validate them like this. You can also define default values for your options in a compact declarative way. As a result, Sysbench can now validate options. If you make a type on the command line, Sysbench will complain about the option being invalid. And of course, bundled OLTP Lua scripts now declare their options and respond to the help command. That is, you can just type Sysbench OLTP .select help, and Sysbench will print the list of all supported options. Another thing provided by LuaJIT and the new Sysbench is ability to call C functions from the system library. Again, as I said, it's possible through foreign functions interface, or FFI for short. It allows calling external C functions and exchanging C data structures between Lua code and C code. And one example where it might be useful is that, for example, if you wanted to introduce some delays in your Lua scripts, then you need a sleep function. And the standard Lua library is quite limited. It doesn't have a built-in sleep function, so you have to resort to some ugly hacks like this. Fork another process with a shell and then call the system sleep command and hope that it supports fractional seconds and so on and so forth. Well, you don't have to do that anymore. You can, for example, use just the usleep or nanosleep function provided by the systemc library. You have to declare the function first, so LuaJIT knows function arguments and the return data value, and then call that function directly. You can also use it to benchmark system calls, for example. This is something I had to do recently. If you need to benchmark the overhead of a particular system call, you can just define a single line event function containing that system call provided by the system library, and that's it. It cannot be easier than that. The SQL API provided by sysbench has also been redefined. It now has this object-oriented look and feel. You first create a driver object, and the type of the driver depends on the command line arguments. It can be MySQL or PostgreSQL, for example. Then you use the driver object to create a connection or connections. And then you use that connection option to execute queries, and then you can disconnect. The new API also uses LuaJIT FFI for better performance, and of course bundled OLTP scripts have been rewritten to the new API. The old API is still available, so your existing Lua scripts will work, but if you want your benchmarks to have as low overhead as possible, you may want to migrate them to the new SQL API. Another thing that is possible with the new SQL API is that you can create multiple connections per thread. One example where it might be useful is when you want to benchmark something with some very high number of connections. For example, René, the ProxySQL author, wanted to benchmark ProxySQL with 1 million of connections. And of course, creating 1 million of threads is not feasible. So you can use this since in sysbench 1.0 you create connections. You can create connections explicitly. You can create as many connections per thread as you want. And yes, so you can benchmark something with a high number of connections with just a limited set of threads. Another frequently requested feature that is available in the new SQL API is result sets. So sysbench 0.5 discarded all results automatically, and that was good enough for most benchmarks, because most benchmarks are not interested in reading results from the server. But some complex benchmark scenarios require processing result sets. For example, link bench. Some people have tried to implement link bench in sysbench Lua, and inability to read and process query results was the main obstacle for that. So it is now possible in sysbench 1.0. This is how you can do that. Basically, you get a result set object from a query, and then you can iterate that object to read rows. Or if all you need is just to read a single row from a query, for example, just to read some status variable or statistic counters, then you can use a convenience function called query row, like this. Latency histograms. So sysbench has always had this internal histogram object, which was used to calculate latency percentile values. But the data structure itself was not exposed to users in any way, which was unfortunate, because I think that latency histograms provide much better visibility into latency distribution than just latency minimum, maximum, average, and percentile values. So I added this option. If you pass double-dash histogram on the command line, sysbench will also print latency histogram as a part of its final report. And the nice thing about it is that there's no extra runtime overhead, because sysbench maintains the data structure anyway to generate percentile statistics, so you get it for free. Error hooks. When by default, when sysbench encounters, when sysbench receives an error from this server, it terminates the benchmark. It provides some special handling for certain kinds of errors. For example, if it receives a deadlock error, which is inevitable in OLTP benchmarks, it just ignores it and restarts the transaction. But otherwise, it just terminates the benchmark. However, in certain cases, you may want to provide some special handling for certain error codes. For example, if you're benchmarking a cluster, a Galera cluster or an NDB cluster, and one of the nodes becomes out of sync, then you may want to wait, ignore the error, and wait for that node to become available again. Or you may want to reroute all queries to another node. So there was a half-baked solution, sysbench 0.5. It was called MySQL ignore errors. You could provide a list of errors to ignore, but it worked only for MySQL, and the action to handle errors was hard-coded. Right? Sysbench just ignored those errors, and that's it. A much more flexible solution is provided in the new sysbench. You can basically define your error handler hooks that decide if a specific error should be ignored by sysbench or not, and on top of that, they can also provide some actions, like reconnecting to the same node, or rerouting, creating a new connection to a new node, and so on and so forth. It's now possible to create custom commands. In the old sysbench versions, there was a predefined set of commands: prepare, run, clean up, and help. In the new sysbench, you can, user scripts can define their own commands. Here's an example. It defines a command called pre-warm, which is basically can be used to load the data set to basically to warm up the cache, database cache. And you want to do that in most benchmarks anyway. But previously, you had to implement something like that in some shell scripts, some shell wrappers around sysbench. Now you don't have to do it anymore. That logic is implemented in the bundled OLTP scripts, and you can use it. Unfortunately, MySQL does not provide any command to force loading a specific table or specific tables into the buffer, NDB buffer pool, for example. So you have to be creative. You have to force full index scan to load the primary key pages and secondary pages and so on and so forth. But at least this is now right in the OLTP scripts. You don't have to implement it on your own. Parallel commands. Most commands except run were executed in single-threaded context, and that was a serious limitation for mostly for the prepare command. But people wanted to generate the initial data set in multiple threads, because sometimes creating the initial data set for a benchmark requires loading gigabytes or terabytes of data that can take hours or even days. So doing it in parallel makes a lot of sense. Now it is possible to define commands supporting execution in multi-threaded context, and this is how you can do that. For example, if you have multiple tables, if your benchmark schema has multiple tables, then you can create and load each table in a separate thread. And this functionality is also supported by bundled OLTP scripts. Custom reports. This is the default human-readable sysbench report, which I think is massively cool. But the only problem with it is that it is a little hard to parse into a machine-readable format for future further processing or visualization, for example. So one frequently and long requested feature in sysbench has been to provide to be able to print statistics in some machine-readable formats like CSV or JSON. It's now possible with sysbench 1.0, and you can do that by defining report hooks. These are functions that receive a data structure or a table in lower speak that contains all values, statistic values that are accumulated by sysbench, that sysbench uses itself internally to display statistics. And you can use the data structure to print statistics in whatever format you want. Here's an example doing CSV. And in this example, it's not any different from the previous one, except that it spits out JSON instead of CSV, using the same data structure. But of course, custom reports can be used for much more than printing statistics in custom formats. You can push results to some external store into a time series database or an SQL database, or you can get custom performance metrics from the operating system or even from the MySQL server itself, now that sysbench can read query results from performance schema, for example, and you can display all those statistics along with the main statistics provided by sysbench. Here's a little artificial example. I just needed something short and simple to fit on the slide. What it does is it queries performance schema from the server for the top weight events and for average latency for that event. And then those values are printed together with the main sysbench statistics. And that's it for user-visible changes in sysbench 1.0. I'd like to talk about some of the things that I'm currently working on or plan to work in the near future. First of all, it's Lua API documentation. The current sysbench documentation is terribly outdated, and Lua API is not documented at all. So I'm quite serious about changing it. I'm personally a developer. I think that the code is the best documentation, but I understand that some people may disagree. And I don't want sysbench 1.0 to repeat the fate of previous sysbench versions, where a bunch of useful functionality was available, but still, many people were shy to use it simply because that functionality wasn't documented. I'm also going to implement other benchmarks like linkbench, IAbench, dbt2 in sysbench Lua, because it would be useful to have all those different workloads implemented with similar interface, with the unified interface and unified reporting format. I'm also going to look into NoSQL benchmarks because it is also a popular request. For example, MongoDB and MySQL protocol. And I'm going to implement some pluggable extensions. As I said, sysbench can now be used as a general purpose Lua interpreter, which means I can implement arbitrary scripts, not just benchmark scripts. To give you an idea of what I'm talking about, here I'm going to show a couple of examples that I'm currently working on. The first one is sysbench tune. One thing that I have to do frequently is to tune operating systems for benchmarks. And it turns out it is a tricky task these days simply because modern CPUs and modern operating systems have too many moving parts that make achieving stable and consistent benchmark results difficult. Just to give a few examples, there are CPU and I/O schedulers, and you want to make sure that they are configured identically across benchmark runs and hardware machines that you're using for benchmarks for an apples-to-apples comparison. There's also CPU frequency scaling. CPUs can now scale their frequencies dynamically according to the load and according to the number of idle cores, which is a nice power-saving feature, but it makes achieving stable results challenging again. There's also address randomization, which is a security feature, but it also makes results unstable in some cases, and so on. So I have a bunch of shell scripts that tune all those settings in the operating system, but I thought it would be nice to implement them as a sysbench extension and make them available for everybody else to collaborate and reuse. This module is inspired by tuned daemon implemented by Red Hat, and also Python has a similar module as a part of its performance regression test suite. Benchmark reports. Another thing that I have to do frequently is to generate lots and lots of benchmark reports containing benchmark numbers, some additional metrics from MySQL and operating system, and some visualizations, some charts. I couldn't find any suitable existing solutions because I think that there's a lot of monitoring solutions available for MySQL, but all of them are focused on monitoring real-time performance production systems. So after some research, I came to the conclusion that IPython notebooks look like the right tool for the job. Well, IPython notebooks are popular in scientific academic communities to do something called reproducible research, when you have some experimental data, plus some code, plus some formulae to transform them, the data, and some text and visualizations. And that looks like exactly what I need to provide benchmark reports. As an extra bonus, they can be rendered directly by GitHub. You can just paste an IPython notebook as a GitHub gist and send the link to another person, and GitHub will render it for you. So what I'm going to implement is an extension called sysbench report, which can be used to generate and publish IPython reports. There's no code yet. I'm still trying to wrap my mind around requirements and some terminology to use here. And now that we're going to have some sysbench extensions, right? The question I had to ask myself was how to publish and install sysbench those extensions. And also, it's similar to another question that I get from users frequently, how to make it easy, how to share custom benchmarks. For example, if I implemented a benchmark for a blog post, and of course I want my benchmark results to be reproducible by everyone, I want to publish it somehow, and people try to merge it into the main sysbench tree. But I don't like this idea because merging all custom benchmark scripts into the main source tree would increase maintenance burden on me, right? I have to document them somehow. I have to update them whenever I change the API, and so on and so forth. So it sounds like we need some kind of central repository of extensions and custom benchmarks, and a package manager to search that repository and install scripts from that repository. Luckily, Lua already has a package manager called Lua Rocks, and the only missing bit here is that is a central hub, a central repository of extensions and scripts. I'm going to use that address. There's nothing at that address right now, but I'm going to put it together and use that address as a repository for extensions and custom scripts. To sum it all up, sysbench 1.0 is probably the most significant milestone in the sysbench development history, but I have even more interesting features and hopefully useful features in the pipeline, so stay tuned. Just in case, there are links to the GitHub project and these slides, and that's it. Thank you. Any questions? Do we have time for questions? Yes. Yes.
Well, first off, thank you. This is a major part of our testing.
Good enough, thanks.
And it's great to see it being worked on again. Would you consider, or have you thought about a way to do a constant arrival rate for queries?
Constant what? Library?
Arrival rate? Generate queries at a constant rate?
Oh, yes, there's the mode called txrate. If you use the txrate option, then you can make sysbench generate queries at a fixed rate, the bounded rate.
Excellent.
Yes, and it also, anticipating a possible question, it doesn't have this coordinate emission problems, the coordinate emission problem that people have been talking for the last years. Basically, if you generate queries at a fixed rate, and the system is unable to respond to that rate, then you're going to wait. But for example, if you generate one request per second, and then system stalls for 10 seconds, then you're going to report, your report will be skewed. It will not reflect that 10-second stall in any way. And that's called a coordinated emission problem. So sysbench doesn't have it because it records the queue time, the time when each request was queued, and then it reports as latency all the time difference between the execution time and the queue time. So it doesn't have it. Any other questions? Okay, I'll be around, so feel free to. I will be happy to answer any questions. Thank you.